So, good evening, students. Good evening, one and all. Am I visible? Am I audible to all of you? Yes, okay. So, we are in chemical bonding and molecular structure, right? So, in last class, we have seen till dipole moment, right? So, we have studied about the introduction part, ionic bond, covalent bond, coordinate bond, and different types of small topics we have seen, and we have completed till dipole moment, bond parameters, etc. So, today we will start with Fajan's rule. Okay. So, what is Fajan's rule and what is the use of it? So, just as all the covalent bond have partial ionic character, ionic bonds are also having some partial covalent character. Okay. So, in each covalent bond, we can find some partial ionic character. In the same way, in all ionic bonds, we can see or we can observe some partial covalent character. Okay, so ionic bond in the sense we have to take an ionic compound in which a cation and an anion will be there. So when you bring these two ions together, polarization occurs. What is polarization? Distortion of the electron cloud of the anion by the cation. Distortion or disturbance of the electron cloud of the anion by the cation is called as polarization. Okay, so this is called as polarization. You can see here there is a difference between the two pictures, right? So here the electron cloud is spherical in shape for anion, whereas here you see it is little bit distorted. So this distortion or the disturbance of the electron cloud of the anion by the cation is called as polarization. So due to this polarization only, each ionic compound is having some partial covalent character in it. Now, how to find out the covalent character for different molecules? So for example, if I take lithium chloride and sodium chloride, here anion is same, cation is different. Now, if I want to find the covalent character, or if I want to compare the covalent character of both these compounds, if I want to compare and if I have to tell which compound is more covalent in nature, then I have to use one relation. Okay, and that relation is size of the cation is inversely proportional to polarization relation. Okay, so if the size of the cation is very less, polarization is more. Okay, polarization is more. If the polarization is more, covalent character is also more. Covalent character is also more. So here you can see that lithium size is very small compared to sodium. So it is having the very less size. Size of the cation is very less in case of lithium plus. So the polarization will be more in that case. Means lithium chloride is more covalent. Lithium chloride is more covalent than the sodium chloride. Okay, smaller the size of the cation, larger the size of the anion, greater is the covalent character of an ionic bond. Okay, size of the cation is inversely proportional to polarization, and polarization is directly proportional to covalent character. Okay, so these two are the relations which you have to keep in mind. So is this clear for all? JNV Ramnagar students, is this clear for you? Shall I move on to the next slide? Yes. Good. Now coming to the size of the anion. So I have taken two examples for you. So one is sodium iodide and the other one is sodium chloride. So in these two compounds, cations are same, but the anion is different. Right? In the previous case, anion were same and cation were different, and here anion is different. Now, size of the anion is directly proportional to polarization, and polarization is directly proportional to covalent character. If the size of the anion is more, then the polarization is also more. Means the covalent character is also more. Now, when we compare iodide and chloride, iodide is bigger in size compared to chloride ion, right? So that is having the more covalent character. So sodium iodide is more covalent than sodium chloride. So, and one more relation is also there. Charge on the cation or anion is directly proportional to covalent character. If the charge is more, covalent character is also more. Like for example, if I take sodium plus and calcium 2 plus. Okay. Now you see here sodium plus and this is calcium 2 plus. Or I can take calcium plus or calcium 2 plus also. Okay. If the charge is more, covalent character is more. If the charge is more, covalent character is more. So that is this relation. Coming to the third relation, the cation with inert gas configuration forms compounds with more ionic character. So what is meant by inert gas configuration? Noble gas configuration, right? In which the outer shell will have completely filled electrons. So now, to understand this, now I have taken sodium plus. So it is a cation now, and it is having inert gas because the number of electrons in sodium is 11, and now sodium has lost one electron. That's why it has attained the sodium plus configuration, means it will have 2 electrons in its K shell and 8 electrons in its L shell. Now it has attained the noble gas inert gas configuration. Okay. Now the cations with pseudo inert gas configuration forms compound with more covalent character. Here the cation with inert gas configuration forms more ionic character, and pseudo inert gas configuration forms compound with more covalent character. So what is that? We can take copper plus as an example. Okay. Now here if I remove one electron from copper, I will have 28 electrons in copper. Okay. In which the configuration is pseudo. Pseudo means false. It is not inert gas, but it is an inert gas configuration, that kind of. Okay. Now this is pseudo inert gas configuration, which is having more covalent character. Now if I compare sodium chloride and copper chloride, which one will have the highest covalent character? This is copper chloride and this is sodium chloride. Both are having inert gas configuration. Okay. But copper chloride is more covalent than sodium chloride. Copper chloride is more covalent compared to sodium chloride. Or you can remember in this way also. Copper is a D block metal and sodium is an S block metal, right? So in that way also you can remember. Mostly D block elements will form covalent compounds than S block. Got it? Clear? Shall we move on with one question? So there are 3 rules, 3 Fajans rule. One is about the size of the cation. Size of the cation is inversely proportional to polarization, and size of the anion is directly proportional to polarization. And the second rule is charge. Charge of the cation or anion is directly proportional to polarization. And the third is D block metal ions will form more covalent compound compared to S block elements. Okay. So these 3 are the Fajans rule. Just keep in mind. So from this Fajans rule topic, you can get some questions like arrange the following in the increase. Which among the following is the correct increasing order of the covalent character of the compounds, or decreasing order of the covalent character of the compound? So in that type of questions you can get. Okay. Now coming to one question. Which of the following cation will show highest polarization? Lithium plus, sodium plus, and potassium plus. So all the 3 ions belong to group 1. Only the size differs. Now you tell me which cation will show the highest polarization. We have studied on relation, right? Size of the cation is inversely proportional to polarization. Using that relation, you tell me which ion will show maximum polarization. First, this is the relation. Size of the cation is inversely proportional to polarization. Which ion is very smaller? Lithium. Very good. Lithium is smaller than sodium than potassium. So the polarization of lithium will be more. Okay, very good. Now, coming to the next topic, next very important topic of this lesson, VS-EPR theory. It is VS-EPR theory. So the full form of VS-EPR is the valence shell electron pair repulsion theory. Okay. So we are going to study about this theory now. It is very important. Most of the following type of questions will be asked from this topic in all the year. In every year, they are asking at least one question from this topic in both NEET and JEE. Okay. So just concentrate in it. It is very easy also. Okay. It is very easy. Don't have to get scared about it. Now, this theory has been proposed by Powell and Sigwick. These 2 scientists only proposed this theory in 1940. Okay, and this theory is based on the repulsive interactions of the electron pairs in the valence shell of the atom. Okay, so we have valence shell in each atom, so in which the electron pairs are located. So among the electrons, there will be some repulsion occurs. So this theory is based on the repulsion that is occurring between the two electrons in an atom. Okay. So if I have to take one theory, mostly all theory will have postulates associated with it, right? So now let us see the main postulates of BSEPR theory. Postulate number 1. Shape of the molecule depends upon the number of valence shell electron pairs around the central atom. Okay, so now I have an atom and this atom has nucleus inside it and it is having some inner shell also, but in the outermost shell it is having 2 electrons. Okay, and I can have one more atom. In that atom, if I can have 3 valence electron. Now the shape of the molecule depends upon the valence electron. If I have 2 valence electron, it will form some linear shape. And if I have 3 valence electron, it will form some other trigonal planar kind of shape. If I have 4 electron in my valence shell, the shape of the molecule can be tetrahedral. So the number of valence electrons in an atom determines the shape of that atom, shape of the molecule. Okay. Now coming to the second postulate, pairs of electron in the valence shell repel one another since their electron clouds are negatively charged. Okay, so we have an nucleus here, neutrons are there, protons are there inside the nucleus, and electron cloud is there. We have n number of electrons, right? So all the electrons are negatively charged. So like charges, what they will do? They will try to repel each other. So this kind of repulsion occurs over there. So this is postulate number 2. Now coming to the third postulate, these pairs of electrons, they tend to occupy such positions in space that minimize the repulsion and thus maximize the distance between. So there is a repulsion between the electrons, right? So during that repulsion, you see here, during that repulsion, those electrons will try to occupy the space in which the distance between them is maximum, so that the repulsion can be minimum. You see here, so this is an atom. So the 2 lone pair of electrons, they are occupying these 2 places. Means there is 180-degree angle distance existing between them. Okay, so they try to occupy the maximum distance between them in which the repulsion is minimum. Got it? Now coming to the fourth point, the valence shell is taken as a sphere. The valence shell is taken as a sphere. You see here, I'll show you the picture. Valence shell is taken as a sphere with the electron pairs localizing on the spherical surface. So this is the spherical surface. Valence shells are occupying that, the electrons are occupying that space, spherical surface at maximum distance from one another. So the 4 electrons, they are far away from each other. You see, they are not closer to each other like this. They are far away from each other. Electron pairs are far away from each other is the fourth postulate. Now coming to the fifth postulate, multiple bond in a molecule is treated as single electron pair and 2 to 3 electron pairs are treated as single super pair. Okay, multiple bond is taken as single electron pair and 2 to 3 electron pairs are treated as single super pair. When 2 or more resonance can represent a molecule, the BSEPR model is applicable to any such structure. For example, ozone. So the resonance structure for ozone is given here. As we all know, ozone is having 2 resonance structure. BSEPR theory can be applied to any of these 2 structures. Okay, we can predict the shape of the ozone molecule by using any of these 2 resonance structures. Got it? So these are the 6 postulates, main postulates of BSEPR theory. Now, along with the 6 postulate, one more very important thing is there. That is the order of repulsive interaction. Okay, order of repulsive interaction. So the lone pair repulsion is more than lone pair bond pair, which is more than bond pair. Okay, don't get confused. It is easy only. I'll take one example and then explain you. So I have taken water molecule. Okay, H2O is the formula for water molecule. Now water molecule has one oxygen and two hydrogen. Oxygen has 6 valence electrons, in which the 2 electrons has gone for the bonding. Remaining 4 are there. In those 4 electrons are present as 2 lone pair. So we have 2 lone pair and 2 bond pair around oxygen. Lone pair are localized on the central atom. They are not delocalized, they are localized. Okay. And the lone pair electron occupy more space. They try to keep them very far apart. Okay. Now there is a repulsion between these two lone pairs, which is called as lone pair repulsion. Okay. And also we have repulsion between a bond pair and lone pair. So this is a lone pair, this is a bond pair. So there is a repulsion. We have 2 bond pair, right? These 2 are bond pairs. That is called as bond pair repulsion. Among these 3, this lone pair repulsion is more compared to the second and the third. Got it? So this order is very, very, very important. Okay. So following this order only, each molecule is taking its own shape and geometry, which we will be discussing in the next upcoming slides. Got it? So the postulates and the repulsive interaction order which we have seen so far is clear to all. Shall I move on to the molecules? Shall we see the shape? So based on six postulates only, the molecule is taking a particular shape. We will discuss those things. Shall I move on, students? What we have seen so far is clear to all. Say yes or no. Give me your response. Jain Viramnagar. Fourth point. Yes. The valence shell is taken as a sphere. This is the valence shell. Okay. It is taken as a sphere in which there are electrons in this sphere. Okay. In which there are electrons. And those electron pairs localized on the spherical surface. This is the spherical surface. This is the spherical surface. And all the electron pairs are occupying or they are localized on this spherical surface at maximum distance. You see the distance between them? They are very far. They are not located like this. 2 electron pair here and 2 electron here. They are not located in this manner, right? So they are very far away, like around 180, like around 180 degree distance between them. This is what is the fourth point. Is that clear now? Okay. Fine. So now we'll go for the tabular column, which is very important for you. So we are going to see the geometry of molecule in which the central atom has no lone pair of electrons. So why it is given like there is no lone pair? So we have 2 cases. We have 2 cases of molecule. So case number 1 is molecule in which the lone pairs are equal to 0. Okay, and the second case is lone pair not equal to 0 system. So first, let's discuss the first type and then we will discuss the second type. Okay, so now we are going to discuss about the molecules in which there is no lone pair present on the central atom of the molecule. Okay, so let's start with this. So the first is number of electron pairs on the central atom is 2, and this is the arrangement of the electron pair you can see, and the geometry of this molecule is linear. If the lone pair is equal to 0, then the shape and the geometry of the molecule is same. Okay. If the lone pair is not equal to 0, then shape is not equal to geometry. Shape is different from geometry. Okay. So the second case I will discuss with you later. So now you concentrate on the first case in which the shape and geometry, they are going to be same. Okay. So the first is AB2 type, I can say. What is the type of this molecule? AB2. So A atom is beryllium and B atom is chlorine. And here in this example, A atom is mercury and B atom is chlorine. Okay, beryllium is occupying the center and two chlorines are linear. Okay, 180-degree angle with each other. So this angle is very, very important. So beryllium has only 2 electrons and all the 2 electrons has gone for bonding. So there is no lone pair. Lone pair is equal to 0 here. Got it? In the same way, HgCl2 also. So the angle, geometry and example is very important. Okay. So they will give you the example and they will give the geometry in the other side. So list 1, list 2 and you have to match the correct list and give the answer. Only match the following type of questions can be asked from this theory and they will ask. Okay. Coming to the next type, AB3. AB3 type. So example is BF3. Central atom is boron. And how many valence electrons does this boron has? What is the total number of valence electrons of boron? Can anyone tell me the valence electron of boron? 1 or 2 or 3 or 4? Very good. It is 3. So all the 3 electrons of boron has been used for the bonding with fluorine. You see here A atom is boron and B is fluorine. So it is occupying the all the fluoride ions are occupying the corners. They are located on the same plane. So it is trigonal planar with 120-degree angle with each other, like a triangle. Okay. And coming to the next type, AB4. AB4 type. So CH4 and NH4 plus, ammonium ion and methane, they are taken as an example. And they are forming tetrahedral geometry. Okay, central atom is at the center and 4 hydrogens are occupying the 4 corners of the tetrahedron. And the tetrahedral bond angle is 109.5 degree. Okay, very important. So have a note of it. So now I will move on to the next type. Shall I move on to the next type? Have you all noted? Okay. The next type is AB5. Example is PCl5. So phosphorus at the center. 3 chlorines are occupying the trigonal plane. 1 chlorine is above the plane and another chlorine is below the plane. So it is forming trigonal bipyramidal geometry with 2 types of bond angles present in it. So one is between this. So there is a plane and 1 chlorine is above, right? So this plane and the chlorine which is above, they will form 90 degree. So here it is 90 degree. And if you see, take this trigonal plane, all BAB bond angle will be 120 degree. BAB bond angle will be, you can see here, it is 120 degree. Okay, 2 different types of bond angles. So 2 90 degree and 3 120 degree angle you can find here. Coming to the last type, AB6 type, example is SF6. So here you can see 4 fluorines occupying the 4 corners. Okay, so like you can take this. So this is, you can take a book or mobile. Okay, so there are 4 corners for a mobile, right? So 4 corners are occupied by the 4 fluoride ion and 1 above and another below. So when you connect all the 4 fluorides which are there on the square plane to the above fluoride, you will get one pyramid kind of thing, but you will have 4 faces above and in the bottom side also you will have 4 faces. So 4 plus 4, 8 face. So that's why it is called as octahedral. Okay. So in the above part, if this is the left face and this is the right face and this is your front face and this is the back face. So like this, below also you will have right, left, front and back. 4 plus 4, 8. So it is called as octahedral. And if you see the bond angle, it is 90 degree. So between this, you will have 90 degree. And when you compare the above ligand and below ligand in the sense that fluoride, when you take these two, they will form 180-degree angle with each other. Okay. So like this, we have three 180-degree angle in an octahedral. So there are three 180-degree angle in octahedral. Got it? So these are the molecules in which the central atom has no lone pair of electron. So the shape and geometry, both are called to be same. Both are same. Shape is also octahedral, geometry is also octahedral. Okay. Now let's see the second case. Now here, this case is the molecules or ions with central atom having one or more lone pair of electron. Okay, we will see that. Central atom can have one lone pair, two lone pair or three lone pair. You will not have molecules which has more than three lone pairs. Okay, three lone pairs. Yeah. So let's see those types. Yeah, first example is AB2E. So this E represents the lone pair, one lone pair. Now the example is SO2, O3. SO2 and O3. Now S is atom A and oxygen is atom B. So AB2, central atom is sulfur and sulfur has, so I don't have power here in my place. So that's why I turned off my video. Once I get my power, I'll just turn on it. Okay. Okay. Fine. AB2. AB2 with one lone pair of electrons. What happened? Just give me. With one lone pair on sulfur. So sulfur is here, double bond O and double bond O. Sulfur also belongs to oxygen group, right? So like oxygen, sulfur will also have 6 valence electrons. In that 4 has gone for bonding, remaining 2 is there. That is present as one lone pair. The same way O3 also. O double bond O, single bond O with one lone pair. Okay. So here, for these two molecules, shape is different from geometry. Shape is different from geometry. And in this column, you can find the geometry and the last column gives you the shape. Now, how to find out the shape and how to find out the geometry? Okay, how to find out the shape? If you see the molecule without lone pair, if you see the molecule without lone pair, it will give you the shape. And if you see the molecule with lone pair, it will give you the geometry. Now, you see the sulfur dioxide molecule without lone pair. Just hide this. Hide this lone pair and you see. You will have bent shape. Okay. But if you consider that lone pair, it is giving trigonal planar geometry. Okay. Trigonal planar is the geometry. Bent is the shape. Is this clear for all? Shall I move on to the next type? Yes. Next is AB3E. Example is NH3. AB3E with one lone pair. Nitrogen. Nitrogen is having 5 valence electron. 3 has gone for bonding. Remaining 2 is present as one lone pair. Now you see the shape. If you don't consider the lone pair, you will get trigonal pyramidal structure. And if you consider the lone pair, you will get tetrahedral. It is tetrahedral in geometry. Okay. Now coming to the third type, AB2E2, water is taken as an example. We have already seen, no? Water, H2O with two lone pair. Just see here, without lone pair, it will give you bent. With lone pair, if I connect all these, I will get tetrahedral. I will get tetrahedral geometry. Okay. Shall I move on with the next slide? Yes. Okay. Just let me know once you are done with it. Okay. Yes. So you're done with it. Shall I move on? Okay. The next type is AB4E. AB4E. So SF4 is taken as an example, which is very important. This type is very important. So sulfur at the center, and it is bonded with 4 fluorine, okay, with one lone pair. 6 valence electron, no? So 4 bond pair and 1 lone pair. And without lone pair, if you see, it will give you seesaw. Seesaw, you all might have played seesaw, no? When this two comes here, this will go like this, and when they come here, this will come down. So it is a kind of seesaw shape. And if you can see this lone pair, you will get trigonal bipyramidal geometry. Trigonal bipyramidal geometry, like we have seen in case of PCl5. So that type of structure you will get. Now coming to the next type, it is AB3E2. Example is ClF3, which the chlorine is having 3 fluorine atoms attached with it, and 2 lone pairs are there. Okay, chlorine's valence electrons are 7, 3 for bonding, remaining 4 for 2 lone pair. Now, if you see this without lone pair, it will give you T-shaped. Okay, it is a T-shaped molecule. But if you consider this lone pair, it will give you trigonal bipyramidal, like in the previous case. Trigonal bipyramidal geometry. Now, shall we move on to the next slide? Yes. AB5E. AB5E. So BRF5. BRF5. Bromine is a halogen again, in which 7 valence electrons are there, 5 for bonding, remain 1 is lone pair. Now, if you don't see this lone pair, it will give you, just connect all the 4 atoms which is there on the square plane to the above atom. You will get square pyramidal shape and octahedral geometry. Octahedral means I have to consider this lone pair, right? So I will connect all the 4 atoms which is there on the square plane to the bottom part also. So I will get octahedral geometry. Now moving on to the last type, XeF4. AB4E2. AB4E2. So xenon is a noble gas, and 8 valence electrons are there for xenon, 4 for bonding, remaining 2 is present as 2 lone pair. Now this is giving square planar shape and octahedral geometry. Just connect everything to the above lone pair and below lone pair, you will get octahedral geometry. Okay. So these are the molecules and its types and shapes, geometries, everything is given to you. Just revise it again and again. You will get used to it and you will not forget. Okay. So among these molecules, ClF3, SF4, BRF5 and XCF4. The last 4 types are very, very important. All the molecules are very important. All the types are very important, but these 4 are very, very important. Okay. So shall we move on with one question? Shall I discuss? Yeah, you have to give me the answer for this. Explain the geometry of SiH4 molecule. Can you guys predict the geometry of SiH4 molecule? Just we need to know the valence electrons of the central atom. That's all. If you know the valence electron, you can get the structure. So we have silicon, right? Silicon belongs to which group? Silicon belongs to which group? Very good. It is tetrahedral. Silicon belongs to 14th group. Like carbon, it has 4 valence electrons. So 4 electron pairs. So the geometry is tetrahedral. Very good. Very good, Ramnagar students. Fine. Great. So we are done with VSEPR theory. So in VSEPR theory, there is nothing much to study. You just have to remember those 6 postulates with that order of repulsion and the 2 tabular column. One with 0 lone pair, and the other one with non-zero lone pairs. Okay, so that's all about this VSEPR. Now next we will jump on to valence bond theory. The next theory of this lesson is valence bond theory. So this theory was proposed by, so any doubt student, any doubt in the VSEPR? Shall I continue with the valence bond? If you're having any doubt in the VSEPR, you can let me know now. Yes, okay. Valence bond theory. So it was proposed by Hitler, that is Walter Hitler, and London, Fritz London. Okay, these two scientists only proposed this. And in the year 1927, these two people have proposed this, and it was further developed by Pauling and some other scientists. But the main characters was these two, were these two. Okay, valence bond. So the name itself says valence. Valence means the outermost shell. The electrons which are present in the outermost shell, they are now going to take part in the bonding, and they are going to give the shape of the or structure of the molecule. Okay, I'll take one example. So you see here, hydrogen molecule. Two hydrogen atoms are coming. Each hydrogen will have 1s orbital in which the 1 electron is present, right? So what is the electronic configuration of hydrogen? 1s, 1 no. So each spherically shaped the 1s orbital is coming, and when they try to approach each other, they are overlapping. The electrons which is present in that valence orbital, they are overlapping with each other to form the molecule H2. To form the molecule H2. Okay, now the nucleus of both the atom is common. Electron is also common to both. Okay, so this is how two atoms comes to form the bond according to valence bond theory. Now, there are two types of forces existing in this. One is attractive force. So attractive force arises between the nucleus of one atom and its own electron. Nucleus of one atom and its own electron. So now I have taken two atoms, A and B. So atom A is having the nucleus and it is having one electron. So nucleus is positively charged and electrons are negatively charged. No. So there is some force of attraction. So in the second case also, there is some force of attraction. In the same way, attractive forces also arise between the nucleus of one and electron of the other. Nucleus of A and electron of B. Nucleus of B and electron of A. Now you see here. This is also a kind of attractive force only because they are opposite charges. No. So two different types of attractive forces are arising here. So like attractive forces, repulsive forces also arise between the electrons of two atoms. Between the electrons of two atoms. So since both are negatively charged, repulsive force will arise between the electrons. And also the repulsive force arise between nucleus of two atoms. Nucleus of two atoms. So totally how many forces I have to set? 4. Between nucleus and its own electron and the other atom also in the same way. You see here, this is A hydrogen, B hydrogen. So this is the attractive force, and this is also an attractive force. So totally there are 4 attractive and between two atoms. So this is the repulsive force. Between two nucleus and two electron, repulsive force will push them apart. Attractive force will bring them together. Okay. So these are the types of forces. Now the magnitude of new attractive force is more than the new repulsive force. So among these two forces, attractive force is dominating the repulsive force. So since attractive force dominates the repulsive force, there is a bond formation between the two atoms. Okay, let's take this hydrogen. So this is the potential energy curve for hydrogen. So now let us start from here. Now here the two hydrogens are far apart. Now they are trying to come closer to each other. They have come closer to each other and they have formed the bond between them. Okay, during the bond formation, the energy of the species will be very, very less. If the energy is very less, stability is more. because energy and stability is inversely proportional, no? So here you see the energy, y-axis is taken as an energy, no? So energy of the hydrogen molecule during the bond formation is very less. So hydrogen molecule here is more stable. Got it? But in the first case, it is less stable because the distance of separation is very, very large. And in the second case, it is coming here. And in the third case, it is forming the bond. The bond length between the two hydrogen nucleus is 74 picometer. And this is giving us the bond energy value. What is bond energy? The energy required to break this hydrogen bond is called as bond energy. So what is the bond energy value? It is 435.8 for hydrogen. Okay, it is 438 and this is the more stable state of hydrogen. And this is the hydrogen value. And if I have to break this hydrogen, this much of energy I have to give, no, bond energy. If I give this energy, hydrogen molecule will break down to give the gaseous hydrogen atoms again. Okay, so this is the potential energy curve diagram for hydrogen. It is there in your book also. You can go through that. Now let us move on to the overlapping of atomic orbital. Overlapping of atomic orbital. So any doubt from the valence bond theory first part? So valence orbitals will come with its electron and they will form the bond. That's all. Shall we see the next topic? Yeah, the next topic is overlapping of atomic orbital. So in the valence bond theory, mainly the valence atomic orbitals are overlapping with each other. When two atoms come closer to each other, there is overlapping of atomic orbital. This statement we all know, right? So during this overlapping, we have three types of overlapping that is being seen. One is positive overlap and the other one is negative overlap. Third is zero overlap. Okay. Now, what is positive, negative and zero? We'll discuss one by one. Orbitals forming bond should have the same phase, that is same sign and orientation in space. If two orbitals have to come closer and if they have to form the bond between them, they should have same sign. Both should have positive sign or both should have negative sign. Okay, and they should have same orientation in space. Then only they can overlap and they can form the bond. Now let's see that. Let's see. So when the phase of two interacting orbital is same, so like here you see p orbital is overlapping with s orbital. S orbital is having only one phase, positive phase. When you come to p orbital, one lobe will be positive and the other one will be negative. So positive only overlap. Negative, positive will not overlap. So this is called as positive overlap, which leads to the formation of bond. And here, two p orbitals are overlapping with each other and the phase should be same. Okay, these two are called as positive or in phase overlap. So here two p orbitals are overlapping in a sideways manner. So this will lead to the formation of pi bond. And here also py orbitals, which are perpendicular to px orbital, they are overlapping and a pi bond is formed. Okay. So in case of positive overlap or in phase overlap, bond is formed. Bond is formed. Okay. Now let's see the negative overlap or out of phase overlap. So when the phase of two interacting atomic orbital is opposite like this. If minus overlaps with the plus, when minus overlap with the plus, bond is not formed. Okay, and this is called as negative overlap. Now what is zero overlap? When the orientation of two interacting atomic orbital is such that there is no overlapping of the orbital. So you see here, p orbital is here, s orbital is coming here. So there is no formation. Here there is no overlapping taking place. No, it is very, very less. So there is no formation. This is zero overlap. One more example. Px is here and py is perpendicular to px. So there will not be any overlapping, right? So this is called as zero overlap. Okay. So clear all the three types of overlap, positive, negative, and zero. Any doubt? Okay. Now let's see the types of overlapping. The covalent bond may be classified into two types depending upon the types of overlapping. One is sigma bond and other one is pi bond. Sigma bond is formed by the head-on overlap of the atomic orbital, or we can say end overlap, end-to-end overlap of bonding orbital along the internuclear axis. It is also called as head-on overlap, or it is also called as axial overlap. Combination of orbitals can be SS, SP, and PP. So these three combinations will give rise to the head-on overlap, and that leads to the formation of sigma bond. Okay, we will see one example for each type. SS overlapping, SP overlapping, and for PP overlap. So in case of SS, the shape of s orbital is spherical. So one s orbital will overlap with the other s orbital and it leads to the sigma bond. Okay, if one s orbital combines with one p orbital, they are overlapping in a head-on manner, right? So it leads to the sigma bond with sp overlapping. When two orbitals are coming with its internuclear axis, then both the head, in the head of both the p orbital, they overlap, they leads to pp overlapping. All these three results in the formation of sigma bond. Got it? Now coming to the pi bond. Pi bond means sideways overlapping. So sideways, p orbital, two p orbital will overlap in a sideways manner, like in the parallel axis, or this is the internuclear axis. If this is the internuclear axis, orbitals will be, they are 90-degree angle with the internuclear axis, right? Lobes are 90-degree angle with the internuclear axis. So they will overlap in a sideways manner to give the two saucer type charged clouds above and below. Okay, that is pi bond, leads to the formation of pi bond. Now comparing these two bonds, sigma bond and pi bond, which one will be stronger? Sigma bond will be stronger or pi bond will be stronger? What is your guess? What is the strength of sigma and pi? Which one will have the more strength? Very good. Good. Strength of the bond depends upon the extent overlapping. So in case of sigma bond, extent, the overlapping area is very, very more. So it has the larger extent of overlapping. So the energy required to break the sigma bond is more. Means the strength of the sigma bond is more than the pi bond. Pi bond, the extent of overlapping is very less. Extent of overlapping means that area. Okay, overlapping area is very less, and there it is good. So there is one difference between sigma and pi bonds. Like for you, it is formed by end to end, that is lateral, and here it forms strong bond. Pi will form weak bond. Orbitals involved in sigma bond are S, and here only p orbital will overlap, and here all the sigma bonds will have free rotation, but here the rotation is restricted. Okay, so there is one p and another p, and this is sigma bond. We can rotate this, but when a pi bond is there, this is a pi bond, right? So you cannot rotate here, because if you rotate, the pi interaction will be broken. Okay, so pi bond is having restricted rotation and sigma bond is having free rotation. These are the points that you have to keep in mind about sigma and pi. Okay, so in VSEPR model, we have seen this relation, valence bond theory, that we have discussed the overlapping of atomic orbital, and we have seen the formation of hydrogen molecule also with potential energy diagram. Coming to the types of overlapping, there are three types: positive, negative, and zero. Coming to the covalent bond, sigma bond and pi bond leads to the formation of covalent bond. Okay, so if you're having any doubt, you can ask me. It's already time. So the next topic we will discuss in the next class. So till VSEPR and valence bond theory, you guys study and try to solve questions on this. Once we complete this chapter, we will try to solve some questions in the class also. Okay. So in the next class, we can start with hybridization. Okay. Any doubt? No doubt? Okay. Thank you so much for listening to the lecture, students. Thank you. Bye-bye.